Hey guys, so 2.2 constant acceleration. So last time we looked at constant velocity, and when we did constant velocity, our velocity over time graph was a horizontal line, if you remember. So what it indicated was that there was no change in velocity. So now what we're going to do is we're gonna look at cases where the velocity does change. So we would end up with a velocity graph like this, and one of the things that we need to differentiate is between our average and instantaneous velocity. Although we'll be using average velocity in physics 1, instantaneous it's kind of important to understand. So, our position, let's take a look at a position versus time graph for a changing velocity. So if I have a changing velocity, meaning that I have some acceleration, what's going to happen is I'm going to end up getting a curve of some sort. So I could have something like this. So I can see that it's not linear, so it's not constant velocity. And if I wanted to think about the velocity, then what I have to do is I actually have to look at tangent lines to the curve. Because if I was to find, the velocity between here and here, I can see that that would be this line that connects them. And that would be my average velocity. But I don't know exactly how fast it's going right at this point. In order to do that, I got to think about the slope right at that point. And the easiest way to think about it is if you were like on a skateboard as you move along the curve, how is the skateboard changing? So you can see as you go up, the skateboard's getting steeper and steeper until about there, and then it starts decreasing. So we have a increasing velocity as we go up, and then decreasing as we go down the other side. You don't have to do too much of that analysis with this type of motion, but just be aware that when we talk about velocity with acceleration, when we're looking at this, we're actually talking about the average of velocity. And so that leads us into acceleration. So acceleration we define thusly. So acceleration is my change in velocity over time. It's the difference, the final velocity minus the initial over time. So it's the same concept, except that now we're looking at the change in velocity over time. And what it is it's going to end up being the slope of the line. You'll see once we get constant acceleration, this graph that you're looking at, this is changing acceleration. Our constant acceleration will end up with a line, but we'll be building the model in class in an activity. So just know that acceleration is the change in velocity over time. So now how could we determine, if I knew the acceleration, how could I determine the velocity? So we start with the definition that the acceleration is the change in velocity over time. And if I let my initial time be 0, then I get that the acceleration is just going to be my final velocity minus my initial velocity divided by time, and I can rearrange it to solve for my final velocity. So that I would multiply this over, and I get ax times t equals my final minus my initial velocity. And then I'm going to add this over to the other side, but when I'm going to do that, I'm going to flip everything around because I like to get my variable by itself. So we have my final velocity is equal to, moving this over, it becomes positive, so I get my initial velocity plus the acceleration times time. And this is your second kinematic equation. So this is the velocity function in terms of time. And if you notice, it looks like, and that makes sense. So on a velocity versus time graph, with constant acceleration, I end up getting a line. So this is constant acceleration. And what you can see is that your slope of your line is your acceleration, because that's going to be your change in velocity over your change in time. So I can get the acceleration from it. And then your intercept is your initial velocity. So very similar to constant velocity, but this happened on the position graph. It's been shifted over now. So we talked a little bit about it in class. So let's look at an example. And Suppose you're sitting on a beach watching a cyclist riding a bicycle on a flat straight road. In a 2-second time interval, the velocity of the bicycle changes from -4 to -7. Describe the motion of the bicycle as fully as possible. So the first thing you want to do when you analyze situations like this is maybe make a little picture. So we know that the bicycle is moving with a negative velocity. So if I take, left to be negative, so this is in the negative direction, then I know that the bicyclist is moving in this direction with a velocity of, begins with a -4 meters per second, and then goes to -7. So the magnitude has changed, it's increased. So I'd end up with a longer velocity vector. So my velocity is now -7 meters per second. And that happened over 1-2 seconds. So we could describe the motion. Okay, so the velocity was increasing in this direction. That means that I have to have some acceleration in this direction. And I know that my acceleration has to be negative because it's also pointing in the negative direction. All right, so then we could figure out some stuff. We could figure out the actual velocity using this equation. So my Vx is equal to Vx naught plus AXT. And so I can move this over. What I'm going to end up doing is rearranging and getting the definition. So I subtract it from the other side, Vx minus Vx naught, and then I would divide by the t, and that would tell me the acceleration. So my final velocity was -7 minus my initial velocity, -4, divided by the time, which was 2 seconds. And that would be my acceleration. So -7 minus, so we get -3 halves meter per second squared. And that would be my acceleration. And it's meters per second per second. So it's really this, meters per second, because it's a change in velocity over a change in time. So my units are meters per second. And so it's like, how much is the velocity changing per second? And we can also just say second squared. It's either one is acceptable. So let's look at displacement of an object with constant acceleration. And so the idea here is that we can get the displacement from a velocity versus time graph. And we can do this for, even if it's horizontal, if it's constant velocity. But the idea is that the area under the curve, that will get me back to the displacement and tell me how far the object's moved. And we're going to build this a little bit, and then we'll develop it into our third kinematic equation. Or rather our second. Well, you'll see. It'll develop. It's an addition to the constant velocity equation. But anyway, the basic idea is that I can take these little slivers of a rectangle at some velocity, and that will tell me the displacement during this little tiny interval. And if I start stacking those over some longer interval and add them up, that gives me the total displacement between these two times. So the area under a velocity graph will tell me the displacement. So let's use that in order to determine an equation. So when you do these, what you're going to end up doing is you're going to end up breaking it out into things that you can find the area of. So I can see that I have a triangle and a rectangle. So if we look at this side of the triangle, then that would be Vx minus Vx naught. That's the length of it, Vx minus Vx naught. And then the length of this triangle is going to be T minus T naught. So the area of the triangle is going to be 1/2 of Vx minus Vx naught times T minus T naught. And we can simplify that a little bit because T naught is 0. So what I end up getting is the area of the triangle is going to be 1/2 Vx minus Vx naught times T. Okay. All right. So then the area of this rectangle on the bottom, well, this side over here is just Vx naught. I know that they write the naught first, but we'll do Vx naught because that's how it looks on your equation sheet. And again, the bottom is going to be t minus t naught, but since it's 0, I'm just going to put t. So the area of the rectangle is equal to Vx naught times t. So now if I add those together, the area of the triangle plus the area of the rectangle, then I get Vx naught times t plus 1/2 Vx minus Vx naught times t. Okay, now there's just a little trick that we have to do here, and it's dealing with this quantity. Remember that my acceleration is equal to the change in velocity over time, or Vx minus Vx naught over t, or delta t. So if I multiply that over, I get ax times t is equal to Vx minus Vx naught. So now I can substitute this value in there. So what I end up with is that my total area, which is going to be my displacement, so x is going to be whatever my initial position was plus this. So this would be my displacement plus Vx naught t. And that part right there you should know from constant velocity, but now we have this piece. So I get 1/2 of axt times t. And since we have a t times t, I can just make that t squared. And that is your full position function with constant acceleration. Okay, so that's basically it. There's one more equation that we'll use. So we did this one, and then I just derived this one. And again, this is just adding on this new term for constant acceleration. But we also have this one, and I'm not going to go through the derivation of it. But what this does is, notice there's no time in here. So if we don't know the time and we have constant acceleration, we would use this, that the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the displacement. So this one, not used as much. These two, yes, all the time. We'll use these a ton. And occasionally this one if we don't know what the time was. But that's it. So we'll build the model in class. I gave you a few questions. I believe that they're mostly graphs. So just so you don't forget, or just to remind you, what we have is the position over time, velocity over time, and acceleration over time. And if you want to move from one to the other, you either look at the slope or the area. So slope is if you want to go from position to velocity or velocity to acceleration. And you use area if you want to go from acceleration to velocity or velocity to position. Okay, so give it a go.